Robo Physicists, through the medium of this video, is presenting its team structure, organization, management, core rover design or functionality, and stability of the rover design in each of the competition tasks for University Rover Challenge 2016. KMC Robo Physicists is a team of 20 undergraduate students pursuing BSc Honours in Physics from Kirodimal College, University of Delhi, with Dr. Sumitra Mohanty, an Associate Professor, as our faculty advisor. In August 2015, the team started in selection procedure for selecting the new candidates to join the team. The very first step for the selection procedure was to acquaint the prospective team members with the team and the competition. Following this, the team conducted personal interviews with the students who expressed their interest in being involved with the team. When the selection procedure was completed, it was deemed necessary to divide the teams into sub-teams which would each focus on a particular aspect of the competition. The sub-teams then divided were chassis and driving mechanism, electronics and communication, robotic arm, and science analysis. The rover chassis is a cuboid structure, 103.4 cm long, 32.4 cm wide, and 16.4 cm high. The fully operational vehicle has 120 cm width, 125 cm wheelbase, and 32 cm ground clearance. The aluminium composite material maintains strength and stability. CNC crafted solid U-shaped blocks are used in the chassis as the main wheel mount. Hollow square tubing of size 2.54 cm and thickness 2 mm was used to fabricate the other parts of the chassis. This ensures optimal strength while allowing some degree of play, thus reducing vibrations on the rough terrain. A stiff joint between the square tubes is ensured by using L brackets. The outer shell is composed of aluminium sheets. The rover incorporates a 4-wheel drive system. Wheel motion is governed by a high-torque planetary geared DC motor with specifications 24 volt, 88 rpm, 128 kg/cm torque. This setup allows a 360-degree rotation of the vehicle at a particular position. The mounts for the motors are attached to the wishbones using cylindrical steel shafts to ensure that the wheel is always perpendicular to the ground surface, no matter what orientation the vehicle may be in. The suspension system is an independent double wishbone setup. Each wheel is attached to dual solid aluminium H-shaped wishbones, which are connected to the chassis using stainless steel shafts free to rotate on the steel bearings, thus ensuring smooth traversing. Damping is provided by a coil spring mounted to a piston-based shock absorber. Spring tension has been adjusted to provide optimum stability and shock absorption capability.
The robotic arm of Infinity One can broadly be classified into 3 parts: the limb, differential gear, and the effectors. The robotic arm is mounted on a rotating platform which in turn is connected to the chassis. It has 6 degrees of freedom achieved using actuators and differential gear. There are 2 linear actuators connected to the robotic arm, the elbow and shoulder actuator. The differential gear consists of 2 gears, both placed opposite to each other, which will facilitate the up and down motion of the effector. Infinity One utilizes 2 effectors for different tasks, namely parallel jaw gripper and a digging effector. For astronaut assistance tasks, a parallel jaw gripper having 2 fingers and an opening of about 158 mm will be used. This provides the effector with extra stability while performing tasks like picking up hammer, cans, etc. The above mentioned grippers work on worm gear mechanism. When the motor rotates clockwise, the fingers move away from each other, thus opening the effectors. For sample collection, a scoop with sawtooth jaw connected to the limbs by a bracket being driven by train wheel mechanism is used. This configuration of the scoop enables the collection of required amount of soil sample for subsequent lab analysis.
The electrical system of the rover controls all the movement and functioning of the Infinity One. The electrical system passes off the power to all the subsystems of the rover, which comprises of motor drivers, camera, video encoding and navigation system. The power supply of the rover consists of 24 volt and 12 volt lithium polymer batteries. The 24 volt battery supplies power to the motor drivers and the 12 volt battery will be used to power the exhaust fans and the nanostation M2. A DC to AC converter will be used for the nanostation M2. Infinity One uses two types of motor drivers. Sabertooth 2x12 which operates at 24 volt and 12 ampere and Citroen MDD 10A which operates at 24 volt and 10 ampere. Drive and robotic arm. Both drive and robotic arm use distributed motor controllers. The drive system of the rover has 4 DC motors controlled by the Sabertooth 2x12 for the front and rear wheels of the suspension system. And the robotic arm utilizes a motor controller for the actuators and 2 more for the end effectors and the rotating platform. The electrical board is kept inside the chassis which has 4 fans to eject heat. To save the rover in event of an unsafe event, the rover has an emergency kill switch button which on pressing disconnects the power. The communication between the rover and the base station will be established using Ubiquiti Rocket M2, with AirMax Omni antenna acts as a transmitter placed at the base station, and the nanostation M2 acts as the receiver mounted on the rover, which can withstand adverse climate conditions. The control input to the rover is through the Xbox controller, which can control drive actions, arm manipulations, and camera control. The Arduino Mega 2560 microcontroller programmed on Arduino IDE is connected to the onboard laptop, which works as the main control system and controls the rover as it receives the signals from the base station. The laptops, one on the rover and the other at the base station, have their programs designed on Python platform to communicate between the base station and the Infinity One. Infinity One uses Logitech C920, which can provide images and video streaming of up to 1080p of resolution. The rover uses a wide-angle lens with the camera that provides a wide view of the field by increasing the view to 120 degrees from 78 degrees. The motor attached to the robotic arm provides the rotation and the sight of 360 degrees. Another camera, Logitech C270, is mounted on the robotic arm to assist the arm functioning. The camera mounted on the chassis will provide a panoramic view of the terrain. Camera being connected to the onboard laptop delivers the footage to the base station. The GPS module GlobeSat G-Star 4 is connected through a USB port to the laptop mounted on the rover. It provides the information about the latitude and the longitude of the rover position to the operator via offline Google Earth real-time tracking software.
The ScienceCast task formed one of the foremost precedents for the team this year. A sub-team dedicated solely to the task was formed that worked according to the rules and regulations of the competition this year. The sub-team interacted with the other team members on a regular basis and kept them aware of the research and knowledge acquired along the way. The team would especially like to thank Dr. Anita Kamra Verma, Associate Professor, Department of Zoology, Kirorimal College, and Dr. Gyan Prakash Sharma, Assistant Professor, Department of Environmental Science, for their guidance under which the sub-team pursued its research. For on-site analysis, Infinity One will be equipped with the following devices: a main camera to survey multiple sites and to search for geographical landforms that indicate the presence of water, a relative humidity sensor which will determine the relative humidity of the soil as it indicates the water retention capacity of the soil and also the water availability in it. A subsurface temperature sensor will determine the subsurface temperature, which is an indication of the biological reactions going on in the soil. As an additional science capability, the rover will test the soil for its pH, using a pH sensor to sense the chemical conditions of the soil. After the contamination-free storage of the sample, the lab analysis will be done. For the lab analysis of the collected sample, following tests have been finalized. Physical classification on the basis of morphogeographical features of the soil will be done. Soil sample will then be tested for the presence of microbial life, which will comprise of the tests for any bacteria, spores or fungal hyphae. The organic carbon content in the soil will be determined as it indicates the organic matter level in the soil. Tests for protein will also be carried out by the team.